It's not muted. Okay, a couple announcements before we get into the material for today. So I was planning on having the grading guidelines, the regrade forms, and all this for you, and then I got a back from my sewage line, and raw sewage started seeping through the walls of my tenant's apartment. Yeah, I know. It was so much fun. So I wasn't even, I got absolutely nothing done yesterday except, sterilizing the walls of my tenant's apartment. And today and tomorrow I'm getting a brand new sewage line, which is like some 50-foot long trench, about 2 feet deep, and 4-inch PVC pipe. Much fun and excitement, but that's my lame excuse for not actually having the grading guidelines with me today. I promise you will have sufficient time to submit a regrade about this last exam. I'm not going to surprise you and have it out, Friday and say, well, spring break ends a 10-day regrade period. So the fourth homework is the if homework. It's out and it's due this Friday. We've gotten some rather interesting comments about this. I'll actually bring them in next Monday. Well, the next Monday we have lecture. The fifth homework is, I'm going to start talking about it today. It will be actually posted on Friday. You'll have 2 weeks to do it because, of course, 1 week is spring break. I will not be having office hours today. So we're interviewing for another teaching faculty position. Myself and Professor Horton are the two teaching faculty folks at here, and Michelle Coe is who's teaching 101E has a 1-year fill-in position. And we're interviewing for another spot for next year, and that talk is beginning in about 25 minutes. So pretty much as soon as lecture ends, I'm going to bolt as fast as I can over there. So if you have any questions, concerns, or comments, we can do it Friday, or we can do it by email, but I won't be able to chat after lecture today. So if there is lab tomorrow, you still have to go to lab. If you are leaving town early or going to the game or something, that's fine. Just email cs101 at cs, the very bottom one, and we will get you scheduled into a lab that better fits your schedule. Friday's lecture is going to be sort of a Q&A type thing. I'm not going to have anything prepared. It's just if people have questions or are a little confused on something, that's a good time to ask it. Pretty much if nobody shows up, which is very well likely, I'll probably leave it about 5 minutes after. So if you're wandering late and no one's here, that's why. In terms of course materials, we're going to get through the majority of loops today. There's some important loop stuff I'm going to cover the Monday after spring break. And then we're going to launch right into methods and classes. And that's going to take probably the next month after spring break. It's actually a fairly long and involved topic. Office hours, all my TAs are on vacation as well over spring break. So the last office hours will be the ones this Friday. I know Professor Coe has them in the morning. Office hours will start up again the Sunday before spring break ends, which is not, of course, this upcoming Sunday, but the following Sunday at about 5 p.m. And let's see, clickers. Everyone has to have a clicker after break. Right now I'm using the clickers for, how would you understand this? And my plan is to start using them for more interesting and useful questions that we'll see actually once we get back from spring break. Questions, comments, concerns? Okay, well, that was easy. So this is homework 5. I'm going to just talk about it briefly. This is the card game War, but we didn't want to actually call it War because we thought we'd get in trouble. So we thought about love, and then we thought we'd actually get in more trouble for that. So we're calling it Peace. In particular, it's a somewhat simplified version. Remember that the way this game works, for those of you who have played it, or the way it works for those who have never played it, is you take a deck of cards and you deal the 52 cards to the two players. Person A gets 26 cards, person B gets 26 cards. You pick up the top card, and whoever's card is higher, they win that particular round, if you will. Then you take up the next card, and whoever's card is higher, they win that particular round. And that's what we're actually going to be implementing in this particular programming assignment. You, the player, are going to play the computer, so the computer is going to be one player, you're the other, and there isn't a huge amount unlike poker, or other games where there's actually the user makes decisions. In this game, there aren't that many decisions made, right? Because the card is dealt out, and you pick up the top cards, whoever wins that one. I mean, essentially there isn't much choice made by the users in the whole process. So there's actually going to be very little input throughout the whole thing. But we are going to provide you with two already written classes for you to use. One is the yes-no extractor that you're using from the current homework. It basically will allow you for the few things that you do for the few things where you do have to make decisions, it'll allow you to do a yes-no decision, and just like for the current homework, it returns either true or false. The other is a card class, and we saw this briefly with the lab quiz. There's a card class that has a whole number of different methods. Basically, a card is defined, you create a card by creating an integer between 1 and 52, because there are 52 cards in a deck. And then, 1 to 13 happens to be the clubs, 14 to 26 happens to be the diamonds. You don't really have to remember all of that, because this class will do it for you. And you can start creating card objects and playing with them. In particular, you can get their suit, get their face, and a lot of the stuff that we've seen in the lab quiz, or that you saw briefly in the lab quiz. So the idea is that you're going to have these card objects, and you're going to create a deck of cards. You're going to shuffle that deck, and then deal them out to the players. It turns out that creating the deck is actually pretty easy. We all know how to use vectors. That was the fun and exciting homework 2. And the reason we gave you that homework 2, as opposed to something that was more interesting, was because vectors are extremely useful. You create a vector, you stick 52 cards into your vector. That's your deck. You then go and you shuffle the vector. And it turns out that shuffling the vector is done by that command. And that's actually written in the homework. And that will take that vector that has all these cards in order and randomly rearrange it. You've now shuffled your deck. And then you go about dealing cards out of your deck. You get the card out of spot 0, and that's the top card out of the vector. The top card out of the deck. So a lot of the code for managing the cards in particular we provide, but a lot of the code for managing the deck, it's essentially a vector. Stick your cards into a vector, shuffle the vector, and then you have your now mixed up deck of cards. So, I mean, that's sort of the brief preview I'm going to talk about here. I don't want to spend too much time on it because we have a lot of material to go through. Any questions or comments about the homework? Okay. So, we have finished up talking about the 3 types of loops that exist within Java. We have the while loop, the for loop, and the do while loop. And for the most part, they're all kind of equivalent. You can convert one into the other. I'm going to show you 2 more commands within Java dealing with loops, break and continue. And then we're just going to start getting into a couple examples. And I have a fairly fun way to wrap up this lecture just in time for you all to leave for spring break. So the first thing that I want to talk about is the continue keyword. This is not a keyword that you have seen before. In particular, anytime Java sees the word continue, when it hits that in a program, it will start the next iteration of the loop immediately. So anything remaining in the loop body is not executed. So it hits the continue and it immediately starts execution of the next loop, even if there is stuff after the continue keyword. Take a look at this for loop. So here, okay, what color am I doing today? Bright green. Sorry, orange was a bit late. So A is going to go from 0 to 9. I'm sorry, 0 to 10. Notice that's a less than or equal to 10. So that loop is going to execute for a total of 11 times. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here it says if A mod 2 is equal to 0. That's checking to see if the number is even. Any even number divided by 2 is going to be give a remainder of 0, whereas an odd number divided by 2 is going to give a remainder of 1. So that's an easy way to check if a number is even. So if A mod 2 is equal to 0, then we know that the number is even, and it's going to continue. What that means, it's going to immediately start execution of the next iteration of the loop and skip that entire line. Of course, if a mod 2 is equal to 1, then it doesn't do that particular if statement, and it will actually print out a as odd. So that's the output. Any even number, any time that the loop hits where a, the loop variable, is an even number, it's going to never get beyond this continue keyword. It immediately starts the next iteration of the loop, at which point a is incremented and is then an odd number. When it is an odd number, this is false. So we don't bother with the continue, and we print out a is odd. So the one thing I want to point out here is that we say that the rest of the current loop is not executed, except the for update is. The way a for loop works is even though we're not when we hit a continue, we're not executing the rest of the loop, we are still executing the a++. Meaning we're going to increment a to the next highest value, which kind of makes sense because if we hit continue and we never incremented a, this loop would never get anywhere. So a is 0, it's going to continue, starts over, increments a to 1. A is equal to 1, it skips the continue, prints out 1 is odd, etc., etc. So that's the continue keyword. Immediately stop execution of the current iteration of the loop and start the next iteration. Oh, sorry. Yeah. Next up is the break keyword. This is the same break keyword that we saw in our switch statement. In particular, it will immediately stop the execution of the loop, period. Continue stops execution of the current iteration of the loop and starts, the next time the loop goes around. Break just immediately stops it. It terminates that particular loop. So consider this code. Again, a is going from 0 to 10, a total of 11 values. If a is equal to 5, break. What this is going to do when a is 0, 1, 2, 3, and 4, this is obviously going to evaluate to false. When a is, so it evaluates to false, it doesn't do the body, and it prints out a is less than 5. When a is finally equal to 5, this evaluates to true, the break is executed, and immediately starts executing down here. So this is kind of like the break in a switch statement. In a switch statement, if we hit a break, we immediately go to the very end of the switch statement. Well, here, if we hit a break, we immediately go to the very end of the for loop and start executing the code right there, which none is listed right now. So there the output is going to list 0 through 4 are all less than 5. Okay. Questions on continue and break? Just by quick show of hands, because I thought I had a clicker slide. How many people feel they understand continue and break so far? Okay, I'm seeing most hands. So what I'm going to then proceed into is a couple examples that show how to tie all of this together, including how to use continue and break. We've seen 3 kinds of loops, while, for, and do while. We've seen the 2 loop commands, continue and break. So first up is for hobos. So in NPR's Sunday morning edition, Will Shortz comes on and gives the puzzler. And he's the crossword editor or the puzzle editor for the New York Times. And he gave this one puzzle a number of years ago that works out well as a good for loop example. So the problem is that for hobos need to split up 20 hours of work. They're wandering wherever they're wandering, and they need to split up 20 hours of work among the 4 of them. So obviously the easy and fairest way to do that is each one does 50 hours of work. But one hobo is more intelligent than the others, and he or she says, well, how about we do this? We're going to draw straws, and whenever number is on the straw, we will do that many hours on that many days. So if you draw a 5, you're going to do 5 hours on 5 days, or a total of 25 hours. If you draw a 10, you're going to do 10 hours on 10 days for a total of 100 hours. So, all right, if you draw 3, you do 3 hours on 3 days for a total of 9 hours. So, not surprisingly, if the smart hobo figured this out and managed to convince everyone else to go along with it, he or she manages to draw the shortest straw, and of course is going to get off kind of easy, as we're going to see. So the question is, how many ways are there to split up the work? How many ways do we split up 200 hours in this particular fashion? And which one did the smart hobo choose? So, as with any program, we need to sit there and analyze it and figure out exactly what they're asking, what we know, and what we have to figure out. So we are looking for integer solutions to that formula. We have hobos A, B, C, and D. A is going to do A hours of work on A days. The next one's going to do B hours of work on B days, C hours of work on C days, D hours of work on D days. And that needs to equal 200. We're only looking for integer solutions of this because there's an infinite number of real solutions, but you can't do 3.5 hours on 3.5 days. It must be integer solutions of it. So we know the following. Each number has to be at least 1. Sure, it's possible to say, 0 hours on 0 days, but even the dumb hobos would balk at that. So each number has to be at least 1. And it can't be any greater than 14. Because if one hobo drew 15 squared is 225, you're already over the 200. There's no positive number that you can add to 225 to bring it back down to 200. So we know that each of those numbers has to range between 1 and 14 inclusive. We don't care about the order. In particular, if we pick 1, 2, 1, 2 as the total number of hours, okay, granted that adds up to like 10. But if you picked 1, 2, 1, 2, that's the same as 2, 1, 2, 1. There are a pair of hobos that are doing 1 hour on one day, and a pair of hobos that are doing 2 hours across on each of 2 days. So we don't actually care about the order either. Okay, so we're going to implement that with nested for loops. And as it turns out, this is the code. It's not actually as bad as it looks. Here we have 4 nested for loops. A, B, C, and D for the solutions to the equation that we saw before. Each one of those is going to range from 1 to 14. So total, we're going to have 14 times 14 times 14 times 14, or about 40,000 possibilities we need to consider. So A ranges from 1 to 14. For each of those values, B is going to range from 1 to 14. For each of those values, C ranges from 1 to 14. For each of those, D ranges from 1 to 14. So those are our nested for loops. Notice that we start at 1, and we end equal to 14, not strictly less than. And then we have this, which is the body of the innermost loop. It says 2 things. This first line and, of course, the second line. Well, the first line says if A is less than or equal to B, and B is less than or equal to C, and C is less than or equal to D. What happens is that, let's say 1, 2, 1, 2 was a solution. That's going to appear many times. It's going to appear, 1, 2, 1, 2, 1, 1, 2, 2, 2, 2, 1, 1. I mean, there's a whole bunch of different ways that it can actually appear. All of those are the exact same solution. A pair of 1 straws and a pair of 2 straws. So what we're going to say by this part here is that we're only going to consider a solution if it's in sorted order. Meaning A is the smallest, D is the highest. Could be that some are equal, but it's only going to consider a solution in sorted order. So this one is in sorted order, right? A is less than or equal to B is less than or equal to C is less than or equal to D. These are not. So the fact that we're saying only consider ones that are sorted, meaning A is the smallest, and B is the next highest, and C is the next highest, and D is the highest, is preventing duplicates. In terms of 2, 1, 2, 1 doesn't fulfill that, but 1, 1, 2, 2 does. So that's what that first line does. It allows us to ignore duplicates, which will appear many times. The next line says, if A squared plus B squared plus C squared plus D squared is equal to 200. In other words, if the integer values in A, B, C, and D all add up to the number of hours of work needed. If so, then we're going to print that out. So this will consider a total of about 40,000 possibilities, all possible combinations of A, B, C, and D, where each one of them is anywhere from 1 to 14. It will make sure they're in sorted order. It will make sure they're solutions to the problem, and if they are both of those, i.e. they're in sorted order and they're solutions, then we're going to print out the values. Any questions so far? How many people feel good with that program? Okay, I'm seeing some hands. Is the sorted order thing confusing? How many people want me to go over the sorted order thing again? Okay. Yes?
Should there be something in it to count up how many iterations it goes through? How many times the thing printed out, so that you don't have to sit there and count?
Well, as it turns out, so the question was, should there be something that counts up the total number of iterations? We certainly could. We could, right there, do something like int count equals 0. And then somewhere in here, put count plus plus. As it turns out, there aren't that many solutions that are going to be printed out, so that'll be easy to count. In terms of what's in the yellow box is executed in 14 to the 4th times exactly, right? Because each part of that for loop is going to execute a total of 14 times. So I think for that reason we probably don't need an int count in this example, but in general we probably would want some sort of counter. So for hobos, oh come on, it's here somewhere. Here we go. And when we run it, we notice that we get all of 2 solutions. So partly it's because I already knew there were 2 solutions. I didn't bother putting in the count. We get the solution 2, 4, 6, 12 and 6, 6, 8, 8. And those are the 2 possible integer solutions to that equation that fulfill that particular property, or the particular properties we talked about. So those are there are a whopping 2 solutions to it, so that was sort of part 1 of the question. And not surprisingly, the smart hobo is going to make sure that the first one is it, and she is going to pick 2. Any questions? Okay, guess what slide's next? Okay, so incompetence. When you earnestly believe that you can compensate for lack of skill by doubling your efforts, there's no end to what you can't do. Those are nails that have been bent and hammered in. Cluelessness. There are no stupid questions, but there are a lot of inquisitive idiots. I don't believe in this one. I'm just presenting it. Ineptitude. If you can't learn to do something well, learn to enjoy doing it poorly. That's kind of like me in snowboarding. Insanity. It's difficult to comprehend how insane some people can be, especially when you're insane. These aren't as funny as some of the others. Okay, so I want to show you an alternate way to implement the inner part of that for loop that we saw in the for hobos. And this is going to use continues and breaks. Or we'll use one of them. So inside the innermost for loop, we had this code, which said if it's sorted, and then it said if it's a solution to the problem, print it out. So I'm going to show you a different way to implement that. First, consider the negation of the first if condition, if it's sorted. We want to negate this. I'm going to show you why in a minute, but I first want to go through the negation. Here we have something and something and something. Remember De Morgan's law for negating it. You change the ands to ors, and you negate each individual clause. So the negation of that is going to be not A is less than or equal to B, or not B is less than or equal to C, or not C is less than or equal to D. This is the negation of that. Well, not less than or equal to is greater than. So the negation of this line up here is just A is greater than B, or B is greater than C, or C is greater than D. Right? Because if any of these are the case, then it's not in sorted order, and this won't be true. Having said that, here's the new code. If it's not in sorted order, which is essentially what that says, continue. Going back a slide, this says essentially if it is in sorted order, then, check it further. This says not in sorted order. So if it's not in sorted order, continue. What continue is going to do is start the next iteration of the loop. If it's not a solution to the problem, notice that we have a not equals there instead of an equals. If it's not a solution to the problem, continue. Otherwise, print out the solution. So what this is saying is that if either it's not in sorted order, bright green, right? If it's not in sorted order, I'm going to hit to continue, and I'm not going to get to any part of the rest of this loop body. It's going to increment D and start the next iteration of the for loop. But let's say it does get through that. It's going to see if it's a solution to the problem. If it is a solution to the problem, 2, 4, 6, 12, then this is going to be false. We're going to hit we won't hit the continue, and we'll go ahead and print it out. So it's a slightly different way of doing it. We're using, the idea is that we've negated the condition. Before we said if it is the case for both, then print it out. This is if it isn't the case, skip to the next iteration of the loop, and we never actually get to the print statement. So we still have to get through the fact it needs to be sorted in order to get through. It needs to be a solution in order to get through, and then we're going to go print it out.
So does this mean that we won't ever be needing nested ifs anymore? This is what we're avoiding.
The question was, does this mean we won't ever need nested ifs? No, you still will need nested ifs. This was just an example that separated it out into separate parts. I thought this might actually be less confusing if they weren't nested, because we've already seen a bunch of for loops nested. Yes?
Why don't you need an else?
You could have an else. In this case, it actually doesn't, it'll work either way. So if I was to say else if, ultimately, if this is, so let's say we had an else there. If this was true, then we're going to skip the rest of the body, and it doesn't matter what's there. If it's false, then it will go ahead and check this, whether the else is there or not. In this one example, we don't need an else. An example such as, for example, your homework, you would need else's. Other questions, comments, concerns? Yes?
So if the first statement is true and it continues on to the equation 1, if that was true, then it continues on to the sys 1.1?
If this evaluates to false. So remember that the way, and if, I think you had the right idea, but if this evaluates to false, right, that evaluates to false when it is in sorted order. Because that's saying if it's not sorted. Well, if it's not sorted, then it'll continue on. So when it is in sorted order, that will evaluate to false, and we won't bother with the continue. If it is a solution to the problem, meaning a squared plus b squared plus c squared equals 200, then the second box evaluates to false, and we don't hit the continue. So we still only hit that if both it's in sorted order and it's a solution to the problem.
So if it's true, then it goes to continue and doesn't keep going anyway?
If this evaluates to true, that means it's not in sorted order. We hit the continue, we start with the next set of values. We're going to start with the next iteration of the innermost for loop, and we're going to try a different set of values. And it's going to test the next set of values and say, is it sorted or is it not sorted? Is it not a solution? And every time we hit continue, we're going to try another iteration of the problem. Other questions? Okay.
Are the variables in this line beforehand, or
They're actually created in the for loop. I'll get to that in a minute. wow. Oh, no, we're up to 87. I was reading the wrong value. Okay. Okay, so that we're going to spend some time going over similar examples. And I think some of this will start moving more towards the left. One of the questions that was asked is, what about variable initialization? Right. Okay, come on. There we go. One of the questions that was asked while everyone was doing the surveys is variable initialization. These, what happens in this for loop, because we say int a is equal to 1, it creates a variable a, sets it equal to 1. So it's both creating and initializing it. And essentially for the inside of that for loop, and of course, the inside of the for loop is everything here. For all of that inside the for loop, that thing is going to execute a total of 14 times for all the values of a between 1 and 14. Similarly, for this b, it's created the inside of that for loop is this part, and that's going to be executed once for each value of b. Let's just answer that question. Blah, 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 blah. All my animations, the motivators. Okay, so we had talked about the Ig Nobel Prizes previously, and I wanted to give, we went over, I forget once or twice, but these were the Ig Nobel Prizes from this past December. And every year they come up with different categories. Again, they award it in things that are, they kind of make up their categories. So ornithology, someone did a study explaining why woodpeckers don't actually get headaches. Nutrition, for showing that Kuwaiti dung beetles are finicky eaters. Apparently, they like the particular type of dung, or certain types of dung, but not other types of dung. I don't know. The question is, why don't woodpeckers get headaches? I don't know, but somebody does. Nutrition, for development of a high-pitched electronic teenager repellent and later ringtones. You've heard the stories that you have these high-pitched sounds that only teenagers can hear, and the idea is that you make this really high-pitched sound and it drives people away from your business if you don't want teenagers there. So then they started saying, oh, let's do ringtones. The problem is that the speaker fidelity of a cell phone speaker is not high enough to actually make that sound. I know because I can hear amazingly high sounds. TV hums drive me up the wall because I can hear it. Anyway. Acoustics, for experiments to determine why people don't like the sound of fingernails scraping across the keyboard. You notice when I did it, everyone cringed. Mathematics, for calculating the number of photos you must take to ensure that almost nobody in the group will have their eyes closed. You know, if I took a picture of the couple hundred people here. Literature, for report entitled Consequences of Erudite Vernacular Using Irrespective of Necessity. Problems with using long words needlessly. Medicine, for medical case report titled Termination of Intractable Hiccups with Digital Rectal Massage. Physics, for studying why dry spaghetti breaks into multiple pieces. Chemistry, for a study entitled Ultrasonic Velocity in Cheddar Cheese as Affected by Temperature. So they basically put sound through cheddar cheese, and if you heat it up more, it goes through faster. All of this you can ask why. Biology, for showing that female malaria mosquito is equally attracted to the smells of Limburger cheese and human feet. I think that's the whole point of the Ig Nobel Prizes is why. Okay. We're now going to talk a bit about three-card poker. Three-card poker is kind of like regular poker, except, not surprisingly, there's all of 3 cards. And this was a programming assignment, I guess, about a year and a half ago. Instead of what we're doing, War or Peace, they did 3-card poker. So the idea was to count how many of each hand are possible in a 3-card poker game. So we start with a standard 52 deck of cards, and there's a whole, keep in mind a 52 deck of cards, we have 4 suits, spades, clubs, diamonds, hearts, and 13 faces, numbers 1 through 13. Well, 1 happens to be called an ace, 11 is a jack, 12 is a queen, and 13 is a king. So a total of 52. 4 times 13 is 52 cards. So there's a number of 3-card poker hands. So we can have a pair that's 2 of the cards have the same face value or number. Flush, everything has the same suit. Straight, there's 3 consecutive cards, 3, 4, or 5. Doesn't have to be the same suit. 3 of a kind, all 3 cards have the same face value. And straight flush, which is 3 consecutive cards, all of the same suit. So for those who are familiar with regular poker, there's obviously a number of hands that aren't listed here. You can't have 4 of a kind with 3 cards. You also can't have a full house, which is 5 cards, a 5-card hand, again, with only 3 cards. So those are the possible 3-card poker hands. So we provided a card class, which is kind of similar to the card class that you're dealing with here. And blah, 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 blah. It's kind of like the card class we saw before. We create an integer, we shove it into the constructor, and poof, we have a card, which, depending on the number, is one of the 52 cards in the deck.
When you guys make the homework, are you making up the deck classes and the card classes? Because those aren't things that pay Java.
The question is that when we make up the homework, so we make up the deck class and the card class. We create we write it ourselves. A lot of times we just copy it from previous semester. So sometimes, it has been made up by somebody here, not necessarily me and not necessarily this semester. How's that for a answer that matters to evolve around? It's not in the JDK, if that's what you're asking. So there's a whole number of card class methods. Whoops. Given some card object, we can get the face value. It's going to return a string A, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Q, or K, which is just the various face values of the card. Get suit returns the suit of the card, which would be for diamonds D, hearts H. Get value returns the numerical value of the card, which is 1 to 13. Equals checks to see if 2 cards are the same card, and toString, that'll actually print it out. Again, these are methods. I'm kind of going over it briefly because I want to get to something before this class ends. But these are methods similar to the ones in the lab quiz and in the homework that you're going to see, that you're going to see out in a couple days.
What's the difference between get face and get value?
Get face, if you have an ace, it's going to return the string A. If you have get value, will return the number 1. Get face will return K for a king, but we're to return 13, right? 13 for get value. So then we had a hand class. The idea of a hand class is a hand held 3 cards. And you create it, you get your 3 cards that are going to be in your hand, and you stick it into the hand constructor. And in particular, the hand class, or the hand object, is going to keep those cards in sorted order. So the 3 cards that you would have in front of you is your hand, represented by a hand class. So just like a vector can hold other things, here this hand object is going to hold 3 card objects, the 3 cards of the hand. Next up, we had a couple of hand methods. And the hand methods get the lowest card, which, of the 3 cards in, it'll get what is the lowest card in the hand, get the middle card, and get the highest card. That determined them based on the ordering, like a king was higher than a queen was higher than a 2. I think ace was actually low in this. So we have our hand object. We've given it the 3 cards that we wanted in it. And get high, get middle, and get low will allow us to get the highest card, the middle card, and the lowest card out of the hand. Is valid. Check to see whether or not it's a valid hand. If you have 3 ace of spades, and there's only 1 deck you're playing out of, I would argue that's not a valid hand. Is nothing returns if that hand is not any of the predefined 3-card poker hands. There's pair, there's 3 of a kind, there's flush, and there's a straight flush, right? 5 possible 3-card poker hands. Is nothing means it's not any of the others. So what happened is that in this particular homework, they had to implement further, they had to implement a number of methods in the hand class. They had to find out, they had to be able to test to see if that hand contained a pair, if it contained three of a kind, if it contained a flush. We haven't seen how to implement methods yet, so I'm going to kind of ignore this. But the thing that I want to point out is this part here. What this does is it will go through and consider all possible three-card poker hands. We're going to have I, J, and K. Here we have I, here we have J, and here we have K. Each of those are going to go from 1 to 52. And what those are going to do is consider all possible cards in the deck. So it's going to go through 52 times 52 times 52 possible iterations of this innermost loop. And it's going to basically check that particular hand and see, is it a pair, is it something else? Here we have counters for each of the possible hands. Is pair, is flush, is straight flush, etc., etc. So if any of these are true, we're going to hit continue. Basically, an integer represents a card in the deck. If all three numbers are 17, well, that's going to be the 4 of spades. All right, I just made that up, but we'll pretend it's the 4 of spades. And if any of the cards are equal, that means there's duplicate cards in the hand. So the continue there is going to cause it to go back around and continue the next possibility. So that basically ensures, those three lines there, ensures that we don't ever consider cards, consider a hand that has multiple cards in it. I'm sorry, has multiple of the same card in it. We create our three cards by I, J, and K. We create our hands. And then we go through and say, if it's nothing, meaning it's not a pair, it's not a three of a kind, it's not a flush, I'm going to increment that particular variable. If it's a three of a kind, I increment that variable. And essentially, it's going to go through every possible three-card poker hand, about 52 cubed hands, and it's going to check to see what the hand is. Is it valid? If so, I'm going to increment the appropriate counter for what kind of hand it is. It's a straight, it's a flush, it's nothing. And then when we're done, we go through and print it all out. And if we were to run this, I know it's kind of hard to see, but it's essentially there's about 132,000 different possible three-card poker hands, about 52 cubed, and that's the split. There's about 100,000 nothings, there's about 20,000 pairs, and the numbers rapidly decrease from there. Yes?
There's no unexpected hands?
No, the thing that happened is that this here says that, if it's not a valid hand, an invalid hand, as far as this program is concerned, is a hand that has multiple cards. The way this particular thing was written is we actually checked for that previously. So we never, there are some hands that are not valid, but they continue on those lines, and it never actually gets to that part.
No, actually, I was talking about the last line.
Oh, here? No, we don't have any unexpected hands. That was sort of an error checking. So if we forgot to, if we didn't implement one of the methods properly, that would just tell us, hey, you screwed up. In this particular case, any card has to be one of those 6 possibilities. Nothing, pair, three of a kind, flush, straight, or straight flush. It can't be anything else. So that's why that's there. Oh, yeah, I was hoping no one would notice that. Notice, I probably should say system.out. I'm going to ignore what ERR is. Okay. So how are we doing the 3-card poker? Okay. So I'm aiming for the fairly well. I think that was a bit better than the previous one. All right. So I wanted to go over one last thing before you all went on your merry way for spring break. And that's all your base all belong to us. So how many people have heard of this, by the way? Okay, some but not all. So it turns out that there's this game called Zero Wing. How many people played Zero Wing? Okay. So Zero Wing came out in Japan. It was an arcade-style game. And then they released this for the Sega in Europe. And they kind of rushed it. And that was the Sega version, by the way. They kind of rushed it, and they screwed up slightly the English translation. And among other things, they wanted to say, all of your star base, we've captured all your star bases. But instead they translated as all your base are belong to us. They have some other rather interesting things like you will not survive, make your time, or somebody set us up the bomb. So it was this internet phenomenon in 2001 and 2002. And basically you started seeing all these pictures of all your base all belong to us. But it turns out most of them were photoshopped. This particular one wasn't photoshopped and was one of the very few that actually was not photoshopped. Most were. But here is actually, so then what they did is they made this compilation of all these photoshopped images. And that's what I want to play to you before you head off to spring break, because it's so funny. These are all the photoshopped images. That's Bill Gates. Have a great spring break.